No, that's right. That's right. The answer is yes. It is competitive. Otherwise, nobody would be deploying this stuff at the scale that they're deploying it at. Now, us as a company, we've only had a pilot line up until now. About the first of the year here, we're going to be able to turn on about 50 megawatts of capacity. And before that, we just had a handful. So, you know, this last year, we've been sold out, and we've sold whatever it is, a handful of megawatts. And we're on Sun with a few of those right now. And those are meeting all specs and producing power, and everybody's very happy. They get whatever it is, 5 to 10% more power out of their module by using our cell versus somebody else's. So this is all positive. You know, the 30 megawatts that Amonex did and the 50 megawatts that just went in China and all this, they're not using our cells yet. So we think that, I mean, basically the math is like this. If you take if we were to sell you our cell at the same price that you're buying right now, but I'm just going to make round numbers here. It's 10% more efficient. You save 10% across everything, right? The whole installation just started putting out 10% more power. So your dollar per watt number went down by 10%, your LCOE went down by 10%, everything just goes down by 10%. So cell efficiency is a huge lever on reducing cost, particularly in CPV systems. Because of the concentration, you can afford to put more technology into the cell, right? The broad area solar technologies, it has to be very cost driven, right? But if you're going to concentrate 1000x, if I can get you another point of efficiency, it's going to save you a hell of a lot of money, so you can pay for a little extra technology. So, you know, all of us can think about inventing new cool little things to improve performance, and it'll actually make sense to do it. Installation is always, I think, the most expensive part, but installation. The pieces of technology are, you know, you have to have a cell. Some people package the cell onto a little coupon, some don't. You've got some kind of a, let's do a Fresnel lens, right? It's a Fresnel lens system. You've got a Fresnel lens. It's, okay, starting from the sun. You've got the sun shining down on a piece of plastic. It's a stamped piece of plastic. It's like this. It's pretty cheap. It's in a stamped aluminum box. Human race is very good at pressing out aluminum boxes. And you've got solar cells sitting at maybe 10 focal points, because maybe it's a 4x2, 8 focal points, 4x2 Fresnel lens module, right? That thing goes on a frame with a bunch of other modules stacked up. Those are just aluminum rods, maybe some steel. It depends on how they do it, but it's most likely aluminum. So that module then sits on a tracker, which is a pole in the ground. So you've got to look at, what does it cost to dig a hole and put a pole? What does it cost to put a tracker on that? What does it cost to put this panel array on top of that? You know, a solar cell is only about 10% of the total installed system cost. So it's only about 10%. So the solar cell itself is probably not the largest cost driver in terms of the money that you pay. But its performance is the largest cost driver in the overall cost of the system in the ground. Yeah. So this is a very good question, and I'm actually glad you answered it. So the way we look at CPV is we are an arms dealer to anybody who wants to buy our cell. Okay? I don't care how many companies go in or out of business. Right now there's about 75 around the world, and the ones who are putting in tens of megawatts today are doing just fine. So what we see is we see our customer base of the leading CPV firms doing just fine. And we're starting to see very large multinational companies who don't really want to have a large profile on what they're doing come online here too. And I've seen their five-year roadmaps on a handful of them. And these players are here for the long haul, and they've done the calculation about what CPV can do in certain geographical regions. And they've done the LCOE and the dollars per watt and all this, and they said, gee, you mean all I got to do is stamp out a piece of metal, stamp a piece of plastic, and buy a cell from Solar Junction? I know how to put stuff on poles. I'm already a solar project developer or whatever, you know. This industry isn't going to go away. Now, we're in a horrible economic situation, and what's happened in the world solar panel market has not been a healthy thing for anybody, other than the people who want to buy hardware at a really low cost. So you as a consumer, it's a good day for you in solar. You can get stuff on your roof cheaper than you've ever been able to. The guy who's selling you that panel may not be in business 6 months from now, right? It's just, that's the fact of the matter. So the way I think about it is those players who've got something truly unique, and I believe we have that, who can survive the next couple of years in solar are probably going to be in a great position to reap the benefits of survival. Today, yeah, it kind of sucks. Now, the other way of looking at it for us in a very myopic way is we don't need a lot of volume to hit all of our targets. Okay? There's whatever it is, almost 100 megawatts or whatever it is that went in this year in CPV around the world. I mean, gee, I'd be just happy as a clam if we soaked up 50 of those. You know, happy as a clam. There's plenty to go around here. It's going to come from solar. Another good example is a lot of places in the developing world. India is a good example. A lot of places in the developing world look at, gee, do I want to buy a really super high technology Siemens plant to produce a flat plate module, hire a bunch of Germans to come into my country to operate the thing and service it, and buy the parts from somewhere else, just basically import all this stuff. Or, hey, I know how to make Saudi Arabia. I know how to make plastic. I pull all the oil out of the ground. Plastic's made out of oil. I know how to stamp plastic. I know how to bend sheet metal. I know how to do assembly, right? Hey, all I have to do is buy solar junction cell from the other side of the world at 10% of the cost of the total system, and everything else can be homegrown. That's a pretty good deal. There are a lot of different ways of looking at how solar is going to grow in different parts of the world, and they're not all uniform. So you've really got to look at everything as a kind of case-by-case, geographic by geographic, political area by political area, which is why CPV isn't going anywhere, in part. We're at lower volume. We're competing with players that produce gigawatts of power or gigawatts of modules, and we're competing with them on a cost-effective basis at 100 megawatt level as an industry. Right? I mean, that has always been one of the advantages of CPV. We already know how to bend sheet metal in super high volume. The semiconductor wafer fab technology that makes this is from 1985. I mean, other than the epitaxy. But the epitaxy is the same stuff that we use to run all the 3.5 chips in our cell phone. So we're not starting, in CPV, we're not starting from, gee, you'd better make custom volume equipment and figure out a custom manufacturing process that nobody's done before. We as a human race have all the equipment and all the intelligence and know-how and whatever to take this already on a cost structure paradigm that's far beyond what our number of megawatts are. And that's basically what's happening right now. So I like to see the day when we're producing a couple of gigawatts of CPV power as an industry around the world, and to really understand where we fit relative to, pick your Chinese supplier that does a gigawatt a year, right? Volume makes a big difference. There's typically a 20% cost decrease for every doubling in volume. I think I got that right. In solar. You can actually look at this amazing chart over the last 30 years. And it's every time volume as an industry doubles, the cost goes down by 20%. It's just, and you look at where CPV is, it's just on a different line. This was flat plate technology. CPV is just on a different line. So, if we can hang on through the next couple of years and we can continue to see, companies doing deployments and gaining some market share, it doesn't take a lot. Our costs will continue to go down. We're going to come out with higher efficiency cells. We haven't touched 4-junction for the most part yet. We built initial stuff as proof of concept. It works fine. But there's a lot left to do. It's growing. This is the thing. There's not a demand problem in solar. If you've got a technology that you can field competitively, there's a market for it. You got to go out and win the projects and get the financing. Yeah, there are some regions of great D&I in China, and one of the funny things is, I don't know if it's funny or not, but there are even programs where they're going to put in all this solar and energy and stuff, and then they're just going to move a bunch of people to go live there. Oh yeah, it's all streamlined. When you really look at what customers are doing, there's really only 2 real flavors of cell that people are going to want. You'll have different cell sizes. So maybe it's 1 millimeter for this guy and maybe it's 8 millimeters for that guy. But as far as the the epi flow and the wafer processing flow and all that, it's exactly the same. It's just a different mask set. So when you look at all of the different, I said, if you can think of a way of concentrating light, people are doing it. This is true. But if you were to just imagine yourself as the solar cell and look up at this thing, look up at the light coming down on you, there's really not a lot of difference. So we're not going to have to carry 10 different kinds of totally different devices. It'll all go through exactly the same processes. We'll be able to grow like a big stack of epi and then say, oh, these wafers are going to that customer and those wafers are going to that customer, and it'll all work. But it's a great question. Yeah, you can. And some customers, you know, have engaged us to develop more custom products for them, and we're very happy to do that for anybody who wants it. But you know, that is probably the next layer of real optimization. Right now, it makes more sense to have streamlined products. And you know, if you're going to do 2 gigawatts next year, maybe you want to go after that 0.5%, because that's a few tens of millions of dollars, right? Today, 2 products makes pretty good sense. Man, you sound like one of our investors. Here, let me give you the pocket lint out of my pocket here. Now, can you do something with that in the next 2 hours? It's like, you know, there's a lot of work that goes. That's what I'm saying. You sound like one of our, literally, we've gotten that question from numerous of our investors at numerous times. Look, our competitors, our 2 main competitors have been working on this technology set for 10 or 20 years. And they were able to get this thing up to 38.5% efficient triple junction solar cells, or just below. It was more like 38 when we started the company. And their product, when we came out with our 43.5 record cell, their product was about 39% efficient, and they'd been at it for, you know, literally almost 2 decades. So the level of effort that it has taken us to get up that curve and get ourselves to a core level of understanding and a platform, a demonstration of a platform, you know, it's taken a lot. Now that we have that, let me give you a good example. How do you measure these things accurately? Yeah, well, that's part of it. It's not my graph. We think we can measure them more accurately than that. We think we understand how to get that error bar down. But it is a beast. It's a beast to measure that stuff accurately. If you can't measure it accurately, you can't engineer it. You know, all of these things have to be done. You've got to train people. You've got to do the simulations. You've got to develop the materials. You've got to install the equipment. You know, all the equipment, you can't just walk into SNF like you can around here and be, oh, hey, look at that. Here's an evaporator. No. You got to go out and you got to raise $3 million to go buy a $200,000 evaporator, and you got to hire an engineer who knows how to install it, and you got to have another guy who knows how to maintain it, and another guy who can run it for you. It just takes time. Yeah, it takes time, right? So don't worry, though. We will get to it. We will get to it very, very soon. If you gave me, my honest to goodness answer to all of the investors when they ask that question is, if you give me more money, I will go faster. That's literally all it is. If I can hire more people to maintain the equipment and keep things going and run 24/7 and all that, we can go faster. You want to be at 46% by, you know, the end of the next year? Hey, great, we can do that. 47, what do you want? Let me just figure out how much it costs. There's no fundamental reason here. We have a technology platform that's capable of all this. We've just got to go through the engineering cycles to get it up that efficiency curve. The whole concentrator stuff, it started in like 1970. Actually, if you go to Saudi Arabia, you can go see the oldest concentrator system in the world. It was installed in 1981. I've got pictures on my cell phone. It's this giant field. All these Fresnel lens concentrators down onto silicon solar cells. It was in 1981, right? It's still in operation today, believe it or not. It still works, which is absolutely amazing, right? But what happened was in the 90s, when we were putting up more satellites, we transitioned off of silicon and onto 3.5 satellite cells. And those satellite cells went from single junction gallium arsenide to double junction in-gap gas, and the efficiency started going up. Those were optimized for the space environment. They were optimized for AM0, not AM1.5D. But that technology was quickly realized that, gee, if you just put this kind of stuff under a concentrator, you can get much higher efficiency. And it doesn't have a terrible temperature coefficient and all this stuff. So then people kind of dusted off the old 1970s and early 80s concentrator work and said, hey, what if we took these really high efficiency cells and put them in these systems? What could we do? Right? So that's kind of the history. So the 3-5 multi-junction cells that we've got here, the history really is these were developed for running space satellites. Does that make sense? In fact, this is a CPV cell, and these are 2 space cells. Right? So they tile these guys together in giant panels, and off you go. So no concentration on this guy, and a lot of concentration on this guy. This is just, I don't even know where I got this. This is like a kid's play toy. This is not what people actually use, but it gives you the idea, right? You know, maybe you designed your cell to be corresponding to one of these at 1000x. That's going to be a really small cell. Maybe your Fresnel lens is bigger. That's going to be a bigger cell. Maybe you designed it smaller so that the heat sinking is better, right? Smaller cells, it's easier to get heat away than a big cell. All of these design trade-offs people are exploring, so to speak, at the system level. So I can't tell my customers what size cell to use. Now there are a couple of standards that seem to be kind of emerging. 5.5 millimeters is one. This is a 5.5 millimeter on an edge chip. A lot of people are using this size cell, but some people use cells that are a few hundred microns on an edge. Some people use cells that are 10 millimeters on an edge. If you want to buy them, I'll sell them to you. If you want to do things at a PhD engineer level where you go in and you hack something together and say, wow, look at that, it's a multi-terminal cell, yeah, we can do that. But when you really want to do things in a bulletproof way, in a very detailed way, in a productized way, that has demonstrably better performance than another product and the cost benefit all works out, you've really got to go about things in a very hardcore engineering team kind of way. It takes a lot of effort to do that sort of thing. And it should last for 25 years. And there's no reason to do it right now. There's just no reason to. With a 3-junction cell, you don't need to. When you get up to a 5-junction cell, maybe you do. Spectral variations, as you increase the number of junctions, the spectral variations that you can see will maybe impact the 3rd cell or something, or the 4th cell, really hard one at some certain time of the year, and so that limits the current and limits the efficiency, and then suddenly you go, gosh, I should break off these 2 cells from these 2 cells to decouple this problem to get my overall energy harvest up. But we're not there yet, so we don't need to deal with that yet.